So far, I discussed about the software stack and anatomy of NVIDIA GPU. So, in NVIDIA GPU, I had discussed about the organization of compute cores on the GPU architecture. We have seen that the compute cores was organized at high level in GPCs. Within a GPC, they are organized in TPCs, and within a TPC, there are 2 steaming multiprocessors per TPC. When we get inside the SM steaming multiprocessor, we have seen some L1 cache, annual data cache, along with there are 4 processing blocks. Within that processing blocks, we have seen that there is L1 0 cache, warp scheduler, dispatch unit, some register files, and some compute units like int32 compute unit, FP32 compute unit, FP64 compute unit, and tensor core compute unit, along with load and store unit and special function unit. Similarly, now I will discuss about the anatomy of Intel GPU. The GPU which I am going to cover is Ponte Vecchio. So, let us start the discussion on anatomy of Intel GPU. Intel GPU families, which is represented by XE, basically it represent several distinct microarchitecture which is developed by Intel to meet very specific needs of different types of computations. Just like you can see here, the first one is XE-LP. LP is low power, and this category of GPUs are integrated GPUs, and they are for graphic purpose. Next one is HPG, high performance gaming. As the name itself is suggesting, this kind of GPUs are designed to provide high frame rate to support the gaming industries or impressive graphic applications. Next category is fall under HPE, or you can, in short we can say HP, high performance. This category of GPU computers are designed to process large volume of data, and it is well suitable for data center and AI workload. Another category is XeHPC. The GPUs under this category is known as GPGPU category, and they are suitable for scientific and engineering simulations. Simultaneously, you can see here the compute capability of this category of GPUs is increasing from downward to upward. As we are going above, as per this diagram, you can see that the teraflops are increasing to petaflop, and for more detail you can refer this particular link for more information. This is a Intel GPU PVC module, because Intel is supporting a modular kind of approach. So, this is a one GPU module, and it is comes under XeHPC. So, this is called as HPC GPU OAM. OAM is OCP accelerated module, and OCP is an open compute project. So, learners can learn more about by referring this particular link. Now, I will come to the subsystem which is developed by using the various PVC module. You can see this is an entire subsystem, and there are 4 PVC modules are connected in a one particular system. So, this is a subsystem we call it, and it is known as X4 subsystem, where 4 PVC modules are connected with the help of XC links. This is the complete GPU compute node. Here you can see, as I already discussed in very beginning, compute units are just a accelerator. Without CPU they cannot work. So, here you can see this is a compute unit, and you can find there are 2 CPUs are there. Apart from that, here in this yellow color box you can see the X4 subsystem modules are connected. So, this is basically forms the entire compute system, or you can say GPU enabled compute system. Now, let us discuss more about the organization of compute cores in the Intel GPU. This is a very high level GPU. Here you can see there are 2 stack. 2 stack means this is a stack 1 and this is a stack 2. Both are exact replica of each other. I will discuss more in detail single stack and what is inside the stack in the next coming slides. This is a view of Intel PVC GPU. This is a single stack. If you are able to recall what we have discussed in NVIDIA GPU at very high level, there was GPC. Similarly, here you can see some compute core units are organized in some blocks, and they call it XC slice. They are calling it slice, and there are 4 such blocks. In NVIDIA we have seen there are 6 GPUs of that particular GPU, but here Intel is almost similar. If you establish the analogy between these two, or you establish the reference between these 2 GPU, you will find that somehow similarities in organization. They have organized in terms of GPC. Intel is organizing their compute cores in terms of XC slice. Apart from this XC slice, it has a global dispatcher. You can see here it functions as an instruction fetch or instruction dispatcher. There is XC link. This XC links, in NVIDIA we have discussed about the NV links. So, this XC links of Intel also establish the mesh network, and it can connect directly to multiple GPU cards from Intel. It has a XCMA fabric. This is a memory fabric. It always provides the high speed and high bandwidth memory interface to the compute units. There is a media engine, you can see here, and it has MFX, MFX, and 3 such units are available inside it. So, MFX is basically supports the graphic functionalities. Suppose you are working you want to work in computer vision kind of application. So, in that scenario, this media engine will always help you to process the image data. Apart from that, at last you can see this is a stack to stack communication medium is provided. Because of this medium, we can establish stack to stack connectivity. This stack to stack connectivity is possible with the help of this stack to stack connectivity interface. So, let us discuss more in detail by taking the XC slice. So, here you can see in XC slice there are some another blocks are present, and these blocks are known as XC core. Each block is known as XC core, and you can say along with that you can say there is each has a rate race unit. Rate race unit is very useful for the graphic workload, and if you count the XC cores in total, there are 16 XC cores in a chosen PVC GPU. So, let us see what is inside the XC core. Let us discuss XC core in detail. If you look inside the XC cores, you will find that there are majorly two components. First one is a vector engine and second one is XME. XME is a matrix extension, and you can think it of as a vector core, which we have discussed in NVIDIA GPU. Now, let us focus on the vector engine, and each vector engine there is a vector registers, and each vector register size is of 512 bits, and it also supports 2 operation per clock cycle with the help of FMA, fuse, multiply and addition unit. Total number of vector engines that are present in XC core is 8. Interesting part is that the performance or number of elements that can be processed by the vector engine is always depends on the size of data type. Suppose I want to deal with single precision data type. So, I have considered here FP32. So, my data type is of 32, each element is of 32 bit. So, in one vector register I can store 16 such elements. Since each vector core has 8 vector engines, so it can process around 128 elements. If I look at number of operations, so because it supports 2 FMA, so I can multiply it by 2, so 256 element can be processed in a single cycle. Similarly, if I look for double precision data element, each element stores 64 bit information. So, here my vector register is able to store only 8 such element, and an entire XC core can operate around 64 elements. If it is FMA, then 128 elements can be processed in one clock cycle. So, you can see it is just 50% of this. But when I start dealing with FP16 floating point operations, the same method has to be followed, and you will find that it is just double of this and it is a 4 time of this. So, let us discuss the Intel architecture terminology changes. Intel has changed recently, they have changed some terminologies. So, in older terminology is execution unit, but now the new terminology they are calling it vector engine, XC vector engine, because XC is representing the series of GPU families, and the abbreviation is XVE. Earlier they used the term systolic to process the matrix kind of operations. Now, they are calling it as a XC matrix extension, an abbreviation they are using it for XME. Next one is the subslice. Instead of subslice, now they are using the term XC core, an abbreviation they are using for XC. The next term they are using is slice, but now they are calling it XC slice, abbreviation they are using for SLC. Next old term they have used for their GPU architectures is tiles. Now they are calling it as a stack, and new abbreviation it is STK. So, this kind of information is useful to keep you updated the changes the Intel has done in their GPU architecture terminologies, and when you refer the documents. So, it will this short or new abbreviations will help you to understand the term what they are referring. So, let us discuss the number of vector engines that are present in XC core, in XC slice, XC stack and XC2 stack, and similarly I will count the number of matrix engines that are present. So, in terms of we have seen that earlier I have started with the 2 stack. 2 stack is just a replica of this stack. So, you can see that we have started this learning process from 2 stack to single stacks to we get into the slice, and within a slice we have seen that there is arrangement of XC core, and within that XC core there are 2 elements are present, vector engine and matrix engine, and each XC core there are total 8 vector engines. Similarly, there are 8 matrix engines was present. If I look at a slice, if you remember there were 16 XC cores was present in one slice. So, if you multiply the number of XC cores with number of vector engines, you will get the actual count 128. So, within a one slice there is 128 vector engines, and because the count is same for matrix engine as well. So, there will be a 128 matrix engine or extended matrix. Similarly, if I look into the stack point of view, you can remember this formula. So, first is the number of slice, then number of XC cores and number of vector engines. These 3 terms you can think it of, and when you multiply, because we have seen that there are 4 slice, there are 4 XC slice were present in a single stack. So, if I multiply that, I will get the total number of vector engines that are present in a single stack, and if you talk about the 2 stack, it is a just doubling of the single stack and is exact replica of the stack. So, you have to multiply with new parameter is a 2. So, total vector engines that are present in a 2 stack Intel GPU is 1024, and same value will be for matrix engines. Next important point is that when we are talking about the vector size per vector engine is 512 bit, but when you are talking about the vector size per matrix engine is it is around 1096 bits. So, this difference you have to always consider when you are dealing with the matrix engines. Let us discuss the terminologies of various GPUs. So, because in this course I have covered only these 2. So, let us focus on these 2 terminologies. So, I have categorized these terminologies in 2 portions. First one is the hardware terminologies and second one is the software terminologies. The first one is both are GPUs. In hardware terminology, the NVIDIA GPUs has organized their compute cores in terms of graphic processing cluster, and within a graphic processing cluster there is a texture processing cluster. Similarly, if I look in that's a comparison, Intel has organized their compute cores in the form of XC slice. You can cut this, so you can think it of XC slice, and within the texture processing cluster there is a streaming multiprocessor in case of NVIDIA. If I do the reference and comparison with NVIDIA GPU, you can find it core. This is a new terminology, it is XC core. Within the streaming processor, if you go inside, there is a compute core, they are also known as CUDA cores. But when we look inside the Xe core of Intel GPU, you will find this is a vector engine. So, this is the hardware terminologies that different two vendors have followed in their architecture. Now, we talk about the software terminologies, we will cover in detail later, but it was a difference in terminologies. So, whenever they are talking about the threads, group of threads, they call it as a thread block. In Intel GPU, they call it as a group. NVIDIA, the 32 threads, group of 32 threads is known as warp. Intel, they use subgroup. In NVIDIA, each thread, the software entity which actually carries some instructions to do some computation, they are known as a thread. In Intel, they used to call it as a work item. NVIDIA GPUs is emulated with SIMT warp, means you can say emulated of SIMD, is not a true SIMD, but Intel GPU you have seen that is a vector size is 512. So, it is a actual hardware level SIMD it supports. Now, in this topic I am going to discuss about how you can calculate the capability of any compute unit. In this topic I am going to calculate the compute capability of GPU. The calculation of the compute capability is important to know the actual capabilities of underlying GPU. So, it will give you the idea what kind of performance you can expect from that GPU. The performance of the GPUs are always calculated in teraflop, or in simple terms I will say that the floating point operations per second flops, but when the computation will increase in mega. So, it will start calling it as a megaflop, gigaflops and teraflops, and these days we are using the word petaflops. So, here I will consider two GPUs from NVIDIA, because as I mentioned earlier my focus will be more on NVIDIA's GPU. So, here you can see that I have taken the two GPU NVIDIA V100 and A100. So, I have all the parameters I have discussed here. So, why I am calculating the SMs per GPU and I am calculating the FP32 core per GPU, similarly FP60 core per GPU, because this is a key parameter or key component rather I will say to calculate the actual performance of the underlying GPU for different data types. If I say here NVIDIA V100 has a 6 GPC and NVIDIA A100 has a 8 GPC. So, you can say that each GPC has 7 TPC, you can multiply these two. So, you will get 42 TPCs per GPC per GPU. Similarly, in for NVIDIA A100 you will get 64 TPCs per GPU. As we know that there is 2 SMs per TPC. So, their SM count is same for both the GPUs. So, you can calculate how many SMs are present in each GPC. So, here there are 14 GPC and in this A100 case it are 16 GPCs are present, 16 SMs are present per GPC. So, now I want to calculate SMs per GPU. So, simply I will multiply these values 14 because I know this count and I have a 6 GPCs per GPU. So, I will get around 84 SMs and in this case I will get around 128 SMs per GPU, because we know that within a SMs my actual compute core exists. So, I will directly focus on this part FP32 cores per SM. So, I have 64 FP32 compute core that is present in per SM. The number is same for both the GPU, but if I look at the count, how many SMs are present in V100 is 84 and 64 is same for both the cards. So, you will get 5376 FP32 compute core per GPU, and if I look at A100, so I will get that there are 8192 FP32 cores are present. Now, look at FP64 per SM. FP60 core per SMs are 32, that is the same for both the unit, both the cards. But if I look at the total number of FP64 cores per GPU, I will get around 2688. At here it is 4096 FP64 cores are available. Now, look at the tensor core per SM. V100 card has 8 tensor cores per SM and A100 card has 4 tensor cores per SM. So, the total count per SM will be 672 and it is 512 tensor cores per NVIDIA A100. Let us discuss the formula, how we can calculate. So, before that, few important points you to be remember in actual calculation, because each core has a capability to some execution units are present just like FAD and FML. If your operations are using or executing either one of it, then there actually it is performing only one operation per thread, or you can say so one flop per cycle per SM. So, in case I am considering here FP32, it has 64 cores of FP32, that is count is 64, and I am using only either FAD or FML unit. So, only 64 operations per cycle is possible per SM. But if I am executing the instruction and it is using FMA, means addition and multiplication both are occurring in a single thread. So, there will be a 2 operations per cycle. So, that is the reason the 64, because my physical cores are 64 and each core is performing 2 operations. So, that is the reason 64 will be multiplied by 2 operations. So, you will get around 128, this is a count operations per cycle it will support. So, whenever we are calculating the theoretical peak performance of any computing device, so we always consider the FMA, means 2 operations per cycle. And if you look at another way, if you are using unknowingly only either this or this, so you are actually achieving only 50% of the maximum capability of the GPU. So, let us discuss the formula how we can calculate the maximum flops. So, what are the important things? You know that first of all you have to calculate the total number of SM counts that are present. Suppose in V100 card this is 64, then CUDA cores per SM. For FP32 you can think it of 64, then it should be multiplied by 2 is a standard, because I want always FMA to be used for maximum flop. And next is a frequency that is always mentioned in the data sheet. SM count also is mentioned in the data sheet, CUDA core is also mentioned in the data sheet. So, flops, you know that what operations maximum, it is also you have to consider 2 flops per core. So, all this information you can get from the data sheet or by running some device query functions in a program. So, let us do the calculation here. So, I know that 3 important components are required for my calculation. So, number of cores is basically the number of SMs per GPU should be multiplied by the cores. This cores can vary whether you are using FP32, FP64 or INT or tensor core. So, this you can see this table. In this table I have taken the information from the respective data sheets. So, here you can see the total count is 80 and here it is 108. FP cores per SM, you know these values, and another important, all this thing I already discussed in a previous slide. So, another important thing I wanted to highlight is GPU boost clock. The normal GPUs always works in normal clock and boost clock. So, you have to always consider the boost clock for calculating the maximum theoretical capability. And this value of peak FP32 when you are not using any tensor operations. So, this is mentioned here 15.7 teraflop as per the data sheet I am talking about. But let us do, while applying these numbers in my formula, I should also get the same number which is mentioned in the data sheet. So, let us see here, first parameter is number of cores, it should be multiplied by the frequency, and third parameter is FMA. So, let us do the calculation for FP32. So, you can see here how many cores are available, 5120 cores is available. So, this should be multiplied by frequency 1.5, it is given in megahertz. So, I have converted into the gigahertz and it is multiplied by 2. So, with that you can see I am getting the value here, it is 15.7 teraflops per second, and this is exactly matching with the value which is mentioned in the data sheet. Simply again do the calculation for FP64. In FP64 performance, if you see that how many FP60 cores are present, it is mentioned only 2560 cores are present. So, frequency and FMA values are same, only the core count has been reduced. This is just half of the FP32 that we have seen in the architecture as well. In per SM there is only 32 core, or if you look at in a process block there is only 8 FP64 cores are available. So, it is 7.8 teraflop per second. So, you can see these values are matching with the calculated value. So, that means it also give you the idea as just as you are increasing the data, changing the data type, because it always required 32 bits and it is 64 bits. So, as you are changing the data type also it is impacting the performance.